is the hypothetical data set that taken from a company. So this data set was taken from a company performance, a survey that was conducted in a company. And they were trying to look at what are some of the variables that can increase performance of the company. For this company, I named this company called XYT Limited. So now the questionnaire was designed in Likert-Scale. The questionnaire was designed in Likert-Scale, and all the responses were keyed into what you call the Microsoft Excel. For instance, if you look at the first response here was on a demographic characteristic of the respondent, and one of these were employees of the company. So the coding system for gender obeyed what you are calling as the dummy recording. You see 0, 1, where 0 was the female, and male were recorded as 1. So we were using what you call female as the reference category. Okay, so now the first variable is called, this first variable in this case was called L1. So the first variable, remember, if you set your questions in Likert-Scale, you will realize that perhaps the first your first independent variable, you have 10 questions. So in this case, I've considered this variable as L1, L2 up to L6, which means there are 6 questions testing one specific variable in the Likert-Scale. Then the second variable was called S1. So this S1, there were S1 up to S10, which means there were 10 Likert-Scale questions in the variable S1. Then again, we had another variable called M, and then we also have a variable called Q, and then we have a variable called P. So all these were 5 variables that we had in our questionnaire, which had a Likert-Scale format. So what we want to do for this class is to be able to analyze this data that we have before us. And before we start the analysis, we just want to transfer this data set to what we call SPSS, so that we can begin the analysis. Now, based on the result of analysis, it will determine the kind of direction we shall take. Remember, we have already said that analysis depends based on 2 things. First is the research design, and number 2 is the nature of dependent variable. And dependent variable can take 2 big broad categories. Number 1 is numeric. The response may come in numeric. When the response comes in numeric, it can either be continuous or discrete, or it can be a response that comes in categorical. So when a response comes in categorical, categorical variables are classified into 3 groups. First is binary, a response that is dichotomous. It comes in pairs, like live and dead, female and male, yes, positive and negative, yes and no. So that is what we are calling as binary. So another case is a response that comes in ranked response. Like in this case, we are dealing with a case whereby the dependent variable is ranked response. It is in Likert-Scale. Like in this case, we are using what we call 5 Likert-Scale, from what we call strongly agree to strongly disagree. So they were in a range of 5. So that is what has been presented with us today, and that's what we want to analyze. And based on this result, especially when we shall be testing what we call assumption, we shall determine which direction, which model is fit for us for this particular study. So I want to bring in the SPSS and the SPSS, and then I shall transfer you back to the SPSS so that we bring in this data set in Excel to SPSS, and then we begin the analysis. So I want to take you, and you need to be very observant on some of the steps that we do before actually you go and run. So that's what I was saying, that it is not always that you must run a multilinear regression. So based on the type of pretest, the assumptions is supposed to dictate the kind of model that you are going to run. Generally, what we are considering as the ordinal measurement, which is Likert-Scale, can be analyzed in 2 perspectives. It can be treated as a number and then analyzed as a continuous variable, where we are going to run what we call multilinear regression model. But that is only after all the assumptions have been met for running multilinear regression model. If not, then we are not supposed to run multilinear regression model, but we are supposed now to run ordinal regression model that fits this specific a ranked response kind of. So I'm taking you to SPSS, then we import what you call that data set so that you can be able to see the procedure that I'm taking, the same procedure that I'd already taken you through. So this is the SPSS interface. I'm not introducing SPSS interface, but I'm just doing what you call importing the data to SPSS interface. So we already agreed that when we want to import data, you come to File, then I come to Open, then you come to what you call Data. You come to this data, I click Data. So once I click Data, I am supposed now to specifically click where that file is. So like in my case, my file is in desktop. So it is in book publication. So I come to book publication, that's where my data set is. So I will come now to change the file type. So this file type is what we are calling as SPSS. So I want Excel. So I come to Excel file type. Then when I click Excel file type, then my data will just come out definitely. Then I come and click it. So when I click, I come to Open. So when I open, the SPSS will bring it into, will bring the Excel into SPSS so that now I can be able to begin the analysis. So you will find something like this, and then you simply come and say, okay. So when you say okay, you come and say okay. So when I say okay, I wait for SPSS to bring the file. So now SPSS has finally brought, yes, SPSS has finally brought what you're calling as the file. So this is the file. It has been brought into my data view in the SPSS. So now I want to begin my analysis. Remember, the first column here is gender, and then all my variables have been arranged in order. L1 is one of the independent variable. L2 is S1, S is another variable. M is another variable. Q is also another variable. But each variable has several questions that were tested. And now I want to begin off. So when I want to begin off, first of all, I will do what's called transformation. I want to transform this my data set so that it can be easy for me to run the various test statistics. So the first, I will come to what you call transform. And when I come to transform, I come and say compute variable. And then I rename my first variable is under L. I will rename it. So I can say this variable is called, for instance, this variable is called technology. So instead of L1, so the main variable was called technology. So I just come even give now the name of technology. So I now look at this second procedure. Who is on? I want you to close.
Can you mute everyone? There's some noise coming from the background.
That is what I'm trying to look at. Where is the origin of this noise? So let me mute.
Just mute everyone.
Let me mute. Okay. So I think now I'm the only one with the power to talk. So the rest you can keep your background in check. So now what is happening is that I've brought in I renamed my variable here under target variable. I've called it technology. Actually, it was technology. So I want to bring all the questions that were set in the questionnaire under technology in the what you call numeric, in this expression called numeric expression. But remember, when I bring them here, I need to get what you call the mean. So I will bring their mean. I add them, but I get their mean. So I just simply come and write mean. When I come and write mean here, I come and here write mean. Then I open up. Then I bring all these questions that you said. So this, the first one was L1. So I bring it here. I put a comma. I bring the second one, comma. I bring the third one, then I put a comma. I bring the fourth one, I put a comma. I bring the fifth one, I put a comma, and then I bring the final question here. Then now I don't put a comma because that is the final one. I put a bracket. So once I've already done like that, I come and say, okay, the SPSS is already. I say, okay, which operations are we? Variable name contains an illegal character. So the variable name that contains a legal character is this SPSS, this one. Then what do they want us to do? Let me say it's even if it is T. Okay. So this is the naming of the variable. It is rejecting that I've not named it well. So I want to say, let me say L transform. Let me say transform L. Transform L. There's now it has accepted. So transform L, it has accepted. So I've already transformed that. I move to the second. I move to the second variable, independent variable. I simply go to transform. I come to compute, but now I need to remove all these operations that I did previously and then rename this one. Now the second variable was perhaps S, so I will come and say transform S. Transform S, and then I bring all the questions, because there were 10 questions in S, I bring them. But now I'm separating with what you call comma. So I bring S, the first one, then I put a comma. I bring the second one, I put a comma. I bring the third one, I put a comma. This operation is going to move slightly fast. 5, I bring I put a comma. The 6th one, I put a comma. The 7th one, I put a comma. The 8th question, I put a comma. The 9th question, I put a comma. And then the 10th question, the final question, now I close the bracket. Then simply I come and say, okay. When I do like that, the SPSS will automatically transform what I want. It's already, you can, I think you can see what has been generated at the end of my operations. You can have a look at it. A transform L, the transform S is already generated. So I move again now to the third variable. I need to transform the third variable. I just simply need to delete these ones, and then instead I need the next one was now transform M. That is the another variable. So I will bring all of them, transform M here. So I will bring all of them from the first question to the last question. So the first one is M1. So I bring M1. Then the second question I bring here, put a comma. The third question I bring, put a comma. The fourth question I bring, put a comma. The fourth question I bring, put a comma. The 6 questions I bring, I put a comma. 7th questions I also bring, put a comma. 8 questions I bring, then I put a comma. The 9th questions I bring, put a comma. And then finally, I have the 10th questions I bring, put a comma, and then do so on to 11 questions. So I close with question number 11. So I close, and then I come and say, okay. I come and say, okay. Then I move to the fourth variable. The fourth variable was Q. I also do transformation. I told you that transformation is very important, and you can never avoid it when you are doing data analysis. You have to learn about transformation. So transform Q. So this is transform Q. So that's the next variable. So I bring the first question in Q. I will go back to where Q is. So Q is here. So I bring the first question, then a comma. The next question, comma. The third question, comma. The fourth question, comma. The fifth question, comma. The sixth question, comma. And then finally, the last question. Now I close the bracket. I close the bracket, and then I say, okay. Close the bracket, and then I say, okay. Then I go now to the final question. I transform the final question, which is Q. I remove all these. Then I bring down my final question, which was like P, but the Q's are here. So I start from this point. There were 13 questions, comma. The next one, I bring comma. Next one, again, I bring comma. I bring question number 5, I put comma. Question number 6, I put comma. Question number 7, I put comma. Question number 8, I put comma. Question number 9, comma, question number 10, comma, question number 11. I separate with commas. Then finally, I bring question number 13, which is the enclosing question. Then I come and say, okay. Yes, so change existing variable. So what I need to do first is to change this transform. I put P. Let me say transform P. Yes, it's refusing when I remember the variable naming. These are now the basics that we already learned. If at all the variable must be unique. Each variable must be unique. It cannot repeat itself. That's why SPSS has told me you must change the target variable before you can proceed with that operation. So you can see now that operation has been successful. So now I've already done all the transformation that I expect. So I just want to take you. Through what the variable. There is TL, there is S, there is M, there is this transform which was Q, and then there is P. So now these are the ones that now I want to begin my regression using these 5 variables. Now, before you begin what we call regression analysis or correlation analysis, what is more important is that I must test for the assumptions of regression and the assumptions for what we call a correlation. And this is now the procedure of testing for an assumption. Now, if the assumptions are violated, in ordinal measurement, remember, the first presumption is that I want to run multiple linear regression model. But if it fails, even if I transform, then it fails, then that is when I'm going to run ordinal logistic regression model. Okay, now what I'm supposed to do here is assumption testing. So what simply I do is I go to analyze, then I come to descriptive, then I
let me interrupt, Peter.
Yes.
There's a way your volume has gone low.
My volume has gone low?
Yeah.
Okay, let me
I'm struggling to listen.
Okay, let me improve. We are saying that now the next procedure is to test for assumptions. The assumptions we are testing here is the main assumption, the assumption of normality. It's upon the assumption of normality that if my data is as a normal, originate from a population with a normal distribution, that is when I can be able to run what we call a multilinear regression model. So I want to test for normality. That's the first assumption that I want to test. And it is the key assumption that determines whether I will go to run parametric statistics or I run non-parametric statistics. So I come to analyze, then I come to descriptive, then I come to explore. Then all my transformed variable, I will treat them as dependent variable. The L, S, M, and this and that, I will bring them as dependent in the dependent list box. Then you simply go to what you call plots, and you click histogram and normality plots with the test. So once you have already done like that, you come and say okay, so that SPSS will generate for you all the test for normality. Remember, we have already said earlier on that normality can be tested using different methods. One of the methods which is more accurate is the p-value test. Then we also have what we call normality test using checking at the skewness and the standard error. And you can also have QQ plots, and you can also have what you're checking at the histogram. And we can also check at what we are calling as box plot to see whether it is having a symmetrically, or it has an outlier. If at all there is an outlier, then we need to go and rectify that outlier. So now the SPSS has already computed for me the result. So I want to take you through the result. So this is the result that SPSS has computed for me. So this is the column for each and every variable. The transform L, you can see the element of skewness and kurtosis. The standard error is 0.184, and this negative 4.21. But I want to rush over. Remember, I told you last time that if you divide the statistic value of skewed value and the standard error, the value you need to get at 95% confidence is plus or minus 1.96. So I'm not going for that. I'm simply running to what we call the p-value test and test of normality. So it is here. So I want to look at whether all these, they meet what we call the condition. So when I come here, I will find that the first variable is significant. Then second variable is significant. Third variable is significant. Fourth one is significant. And this is also significant. What we are looking for here is that a situation whereby the p-value is non-significant, so that we can conclude that my data set originate, all the variables originate from, we have a normal distribution. So this simply indicates that we don't have a normal distribution in all these case scenarios. So first investigation may be, can the non-normality is as a result of an outlier? So I go and check box plot. It's also given down here. So this is the histogram. This is QQ plots. This QQ plots. And then I first check the box plot for the first variable. So you see it's not symmetrically divided. Okay. And then there is no outlier. If it had an outlier, then we needed to change the way I already talked about how to change your outlier. So we needed to change, but in this case we don't have an outlier. So I move to the next box plot. I move to the next box plot to check if at all it is somehow symmetric, and in case I have the presence of outlier. So I move next. Then I find that I don't have outlier, the extreme values. There are no extreme values in my data set, but my data set is not normally distributed. So that is the first condition, is that my data set is not normally distributed, but I don't have an outlier that can cause what we call a distortion to my data set. Now, what now remains for me? What now remains for me is to ensure that I go back to my SPSS. I go back to my SPSS with the transformed variable to now transform them so that I can test again if at all the normality can be guaranteed. I can now get my data set, now can be, the data I'm going to use to do the computation is now normally distributed. Now, what I can do now with this data is to do what we call, I now take log values. I want to now transform them using what we call logarithm. And I will test on the log values if now it is normally distributed. If it fails that, because logarithm transformation is more powerful transformation on normalization of data. So I will move now again to transform, compute variable. I remove all what I was doing previously. And then now I want to do what? I want to bring in log. So I will bring in, this is log transformation. So when I want to do what you call log transformation, the first step that I need to go is come and click what you call all. You come and click there, and then you come down here, look for what you call logarithm to base 10. You come and look at logarithms to base 10 down there. I will get log to base 10 here, and then I'll bring it up. So that's what you start with. Then now the data, the variable to be transformed, you bring it there. So like for instance, in my case, the first variable that I want to transform is called transform L. So I bring in transform L, I bring it inside there, and then I say, okay. So now transform L, I have to name this variable right now. So this one I will simply rename as, now let me try to rename it as technology if it will agree. It has agreed. Okay, I go again and transform the second variable. I go again and transform the second variable. So my second variable is I need to give it the name here. The name I want to say it is apply. It is apply. Okay, it is apply. Then I simply bring that s variable in which I had used previously. S, I bring it there in the middle. Then I say okay. To move very fast. Then I bring again the third transformation I'm doing using logarithm is now marketing. I do marketing. I bring marketing. Then in the marketing, I just bring in now the marketing variable, which is M transform. I say okay, and then I go again to transform quality. I go again to transform quality. I come here and say quality. So when I say quality, I remove what was there before in the logarithm. I bring now S. So S is simply this one here. I bring it and then I say okay. Okay, that one I've already done. So I move again to transform the last variable, which is now performance, So I remove what I did previously there, and then now I bring in the performance variable combined. The one, it was P here, so I bring it here, and then I say okay. Now I go to my data set in the SPSS and I check that column that I've generated. And then I now test on this variable: technology, supply, marketing, quality, and performance. This is a study trying to establish the influence of technology, supply, marketing, quality on operation performance of a company. So what I want to do here is now I want to use this my variable for running what you call running my regression. But before I move to choose the type of regression I want to run, I want to ensure that I'm working with the data with a normal distribution. If it fails, if this one fails, then now I will not proceed with what you call running parametric statistic, and I go to what you call non-parametric statistic are the ones that I will run right now, because I've done now the most powerful transformation and the transformation has failed. So let me confirm whether it's failing or not. So I go back to analyze, descriptive, then explore. So when I'm at explore, I bring in all the independent transformed variable with the logarithms. So I've transformed them with the logarithms. All of these ones, I gave them their full names. So I bring them, I treat them as dependent. I bring them to dependent list. Then I simply come to the plots, then choose histogram and normality plots with the test. After that, say continue. Then come and say okay, and wait for what you call SPSS to generate for you what you call the output. So in the output that SPSS is going to generate for me, I interpret. If it's still non-significant, then I go and begin straight away to doing what you call non-parametric statistics. Okay, the result, as the result comes, let me wait for the result. Yes, result has not come, is when it is being generated. So let me share with you the result. Let me share with you the result now. I share with you the result. So this is the result that the output SPSS has generated. Let me see the output that where it has started. Where it has started. Yes, from here is where it has started. But I'm just moving to what you call this test of normality. I'm going direct to this test of normality. And if I look at all this, my variable, technology, supply, marketing, quality, they still indicate significant value, which is a deviation from what I was looking for in this normality test. Because normality test, I'm looking for non-significant. So what value of P? So in this case, it simply confirms to me that my data set does not or observe normality. So when a data set is not, when my variables do not originate from a population with a normal distribution, the only option I have now is to go and run a model called Ordinal logistic regression model. So that's what we want to move to straight away, and we are going to run it. So and which are the values will I use? Now, for this, the best values that I needed to use in this instant is, if at all I had coded my variables, especially the Likert-Scale, I'd given it in terms of it could have done much better if at all I'd coded them in what we are calling as dummy I would use what you call dynamic coding, where I start with perhaps strongly disagree as 0 until strongly agree as 4. But nonetheless, I will run it with the way my data was coded, and especially with the computed value. Remember, I'm not going to use the transformed values. The transformed values were only supposed to assist me so that I use those values if at all I know I was trying to make my data so that it has a normal distribution. But all along I've gone through and it has failed. So I will just use with what you call the let me take you to the data set again. Let me take you to the data set again is here. So I will not use the transform values, but I will reuse the values that I computed first. So what were the values that I computed first before the transformed values? All these, they are the ones that I'm going to use in running this. And remember, in this my regression, one of the variables is categorical, gender, which was coded as 0 and 1. So I also need to include it in the regression model. I need also to include it in the regression model. There are several ways by which you can run what you call ordinal logistic regression. The first one is just simply to go to analyze, then you go to regression, then you come to ordinal, come down here to ordinal, there's binaries, ordinal, and click OK. So once you have already clicked OK, you bring in your dependent variable. You bring in your dependent variable. For instance, this is my case, my dependent variable is P. I will bring it down there. Then we have what you call factors, and we have what you call covariate. Now, your independent variables that are categorical, you bring them to the factors column here. But your independent variables that are treated like the continuous one, you treat them as what you call as the covariant. So I will bring in what you call gender as factor. I will bring in gender variable as factor. Come and click, I bring it as factor. Then the rest of other variables that are my key variables in this study that I'm trying to examine, I will treat them as, this is the first one, the second one, the third one, the fourth one, and the fourth one. Okay. These ones were transformed values. Were they the values that I used? Okay, M. Okay, I don't want technology. I want, did I transform the data called P? Where is P? Transform P. Did I transform P? Because I need to bring it, because it is my, okay, I've already brought it in the dependent variable. So I bring the rest. So this is L, Q, S, and M. I bring them as covariate. Then I come and check the option. I'm so much interested in the output. Yes, I click the goodness of fit statistics. I click the summary statistics. I click the parameter estimates. Okay, so those are some of the information that I require. I click, and then I come to click perhaps the scale. I bring the scale, and then I'm supposed to bring in all my scale models. So what are the scale models? Scale models are L's, M, where this scale is means, and I bring them to that box. I say continue. Then what is in the option? Okay, maximum, these ones are okay, that's correct. So after this, I just come and say okay, and then I go and interpret my output. I come and say okay, and then I go and interpret my output, what the SPSS has generated for me. Then now I take you through what we call the interpretation. Okay, so let me take you to the interpretation now. Let me take you to the interpretation of the model. Okay, so it started here. It starts here. Ordinal regression. I'm told. Oh, okay. Let me admit Dr. So I want us to go direct to interpreting my the tables that I've generated, because these are the same tables that you will generate. And the first table that we start with perhaps is case processing summary. The case processing summary is giving me the various percentages for my key variables. Like these are the this is what you call the independent variables. These are on the dependent variable. We also have what you call gender here. And now the mains for the start is what you call the model summary. This is equivalent to my model in when we are running multilinear regression model. So this model fitting information, this is the most important table that perhaps we need to start with. So the model table, there are two information that you are getting here. You need direct to go and check the significant. Is my model significant or not? So this information you are going to get it here. Like for instance, in our case, our model is not significant. Our model is not significant because the p-value is greater than 0.05. Okay, then there's what we call intercept only. This intercept only is the model without bringing the predictors. Model without bringing the predictors. Yeah. So now in the model, we are testing whether are we rejecting what we call our null hypothesis, or are we rejecting the null hypothesis, or we shall go for what we call the alternative hypothesis. What is this null hypothesis? The null hypothesis assumes in the model that there is no significant difference between the base model and the final model when we bring the predictors. Now, when you bring technology, you bring supply, you bring marketing, you bring quality. When you bring it, how does it influence what you call the model? What does the predictors, how does the predictors influence the model? The predictors in this case has non-significant influence to what you call the model. That is what we are reading here, with a p-value having greater than 0.05. Now, in this case, now, if we had a null hypothesis that there is no significant difference between the intercept only model and the final model, what are we now doing? Are we accepting, are we rejecting the null hypothesis? Or
no, you don't reject it because it is not significant.
That's true. So what are we concluding between the intercept only model and the final model? How do they relate?
They are not related.
Yes.
It doesn't significantly contribute to the model, so it means our null hypothesis that says that they are not related wholes.
That's correct. Then now we move to the next table. We link to the next table, and this table is goodness of fit. Goodness of fit table. Now, in the goodness of fit table, what we are looking for is that the person value here, we require it to be non-significant. We require it to be non-significant. Like this case, we find we have what we call the chi-square value of 651.902 and degree of freedom 679, and we find here is non-significant person's coefficient, and that is the value that we are looking for. Now, what is the null hypothesis under what we call goodness of fit? We are assuming that the null hypothesis, the observed data, our observed data in goodness of fit in this case, if at all we our observed data, we are looking at our between observed data, it is having what you call is it having what you call a significant fit? Is it a significant fit of our model? That's what we are trying to look at in the goodness of fit. So we are seeing that the p-value in our case is greater than 0.05. Yeah, and now that is the value that we are looking for. But now, in goodness of fit, what is our hypothesized null? What is our null hypothesis here? What is our null hypothesis? The null hypothesis. What is our null hypothesis in what you call goodness of fit? Goodness of fit. Our goodness of fit table. Or in the first case, I needed to tell you what actually the goodness of fit does in that model. Okay, the goodness of fit table, it has two things that it contains. Number one, there's what we call divariance and then Poisson chi-square test. These are very useful for determining whether a model exhibits good fit to the data. Now, non-significant test results are indicators that the model fits the data well, while the opposite is also true, which means significant test on the goodness of fit simply means that the model does not fit the data. So in this case, what we are we? What are
again,
we,
please, Peter.
I come again.
Repeat what you just said.
Now, the goodness of fit table, in the goodness of fit table, it contains two parameters that we are trying to look at. One is called Poisson's, another one is called divariance, as you can see from the table. So now the Poisson chi-square test are useful for determining whether a model exhibits good fit to the data, whether a model exhibits good fit to the data. Okay, non-significant test results are indicators that the model fits the data well. And then significant p-value indicates that the model does not fit the data. So if at all now we want to report on what we call our chi-square, for instance, in this case.
Okay, sorry, Peter, please go back again.
I go back again. Now the
please,
goodness of fit, we are trying to look at now our goodness of fit table. We want to interpret our goodness of fit table. Now there are two readings here. There is Poisson chi-square test, and then there is what you call divariance. So these are useful for determining whether a model exhibits good fit to the data, whether a model exhibits what you call a good fit to the data. Now, non-significant test results are indicators that the model fits the data well. The model fits the data well. Significant test, which means p-value less than 0.05, indicate that the model does not fit the data well. Okay? Are you able now to understand?
Yes.
Okay. Then now what we go and read, we can now report on what we call as the chi-square value. For instance, the Poisson chi-square, the Poisson chi-square result there, we are seeing the degree of freedom. What is the degree of freedom you can see there? What is the degree of freedom?
679.
Yes.
Yes. So now the chi-square you put in bracket degree of freedom of 679 is equal to, what is the chi-square value are you able to read there?
651.902.
Yes. So you put now the chi-square, you put that chi-square, then you say the degree of freedom, you give the value for the degree of freedom, and you read that value of person's chi-square. Then you put a significant value. Like now, what is the p-value? What p-value do we have there?
0.766.
Which simply means that it's non-significant, and that is what we are looking for. To deduce that my data, to deduce that my model fits the data very well. Fits the data very well, isn't it? Okay.
Yeah, it is.
Then now we can be able now to move to the next table. We can be able to move to the next table, and now this next table is called pseudo R square. The next table is called pseudo R square. So I bring it down here. Okay. And then so that you can all see it. Now this pseudo R square is equivalent to the R square in multiple linear regression. And just a recap, what does R square reflect in multiple linear regression? When you have R square value of 0.67, what does it tell you? Can somebody tell me, what does a R square of 0.67 tell you? And these are the remaining components for us to have one. Or what is the significance of that value? The difference, 0.6 R, my R square, if at all I've got R square is 0.67. How can you interpret that one? Because we want to relate it with this case now. Yes. What can somebody tell me the interpretation of that?
It means 67% of the variability in the dependent variable is accounted for by the independent variables.
Good. I think everyone has understood what he has told us. Yeah? That 67% of variability can be accounted for in what you call the changes in dependent variable is being caused as a result of the combined effect of independent variables. So now when we come to what you call ordinal logistic regression, the equivalent for that R squared, we are calling it pseudo R square. Now in this, we have values that we are presented with at least three readings. The first reading is called Cox and Snell. Next is Nagel, and then FC Faden. These are pseudo R square values that are treated as rough analogous to the R square in the OLS, the ordinary least square regression.
Yeah.
They are treated in the same manner. In general, there is no strong guidance on which reading are we supposed to go for, as per different authors have come up with. But the general one that mostly they prefer is the Nagel, and the value that perhaps we are reading now, we are supposed now to read to present for our report is like now the 1.158 is commonly preferred among what you call researchers, that they present the result for this one called Nagel-Kerr 0.158. But now they say that now the value for this Nagel-Kerr is supposed to have 0.7. A lesser value simply reflect that perhaps there were some variables that we needed to include into the equation. But there has not been very general consensus on this concept of the pseudo R squared. So immediately we are through with what you call in presenting the result of Nagel-Kerr, we are supposed now to move to what you call the coefficient table in multiple linear regression. In this case, we are giving it another name. And the name we are giving it is called parameter estimates. The parameter estimate that you can be able to see also in front of you, the parameter estimate. Now, this is very important because this is where we are going to interpret how each and every independent variable is influencing what you call the dependent variable. Yes? So the parameter estimate, we have what you call regression coefficient. This is like the regression coefficient. And we are so much interested in looking at their significant equivalent. We shall be looking at each and every value or independent variable, and we are concerned whether the change that the independent variable causes to the dependent variable is significant or not. And we are so much particular because here, I told you, because this is a probability model, we shall be interpreting it with regard to what you call the odds. Yeah. So, for instance, so we are supposed to interpret what you call the big coefficient. You remember where it is written estimate. You will find some values which are either some of the variables, like in this my case, I'm so much concerned about the variables that are positive and ones that are negative. So we want just to bring you forth so that you can be able to understand the various interpretation of this. Now, here is, we are seeing that we have the first one, we have what we're calling as the dependent variable. Then we have trans L. This is the technology. The technology, we have supply, we also have what you call marketing, and then we have what you call the quality. And then we have here the categorical independent variable, which was gender. And remember, gender was coded as 0 and 1. Now we are using a 0, which was perhaps we are referring this to be male as my base category. You can see that. Now, I want us to interpret this, how the odds of technology, supply, marketing, and the quality with regard to, and also the gender component, how they impact on to the dependent variable. So that's what I want to take you through. And you shall be reading for me the values that you are seeing there. And first of all, I want to tell you that now we have the parameters, the estimates that are positive, and then we have the estimates that are negative. For instance, we have the first transform L, the estimate value. Are you seeing positive or negative? What are you seeing there? Yeah?
Negative.
Negative.
It is negative, isn't it? So
Yes.
if it is negative, then what are we going to say? For every 1 unit increase on technology, there is a predicted decrease of negative, what is the value there?
2.21.
Negative 0.21 in the log odds of falling at a higher level on the operational performance. Now, this simply means as the scores of independent variable increases, there is a decreased probability of falling at a higher level on the dependent variable. That is the meaning. But when we have what you call a positive, when we have what you call estimate of a positive, then our interpretation is supposed to be for every 1 unit increase on the independent variable, there is a predicted increase of that value in the log odds of falling at a higher level on the dependent variable. As the scores of that independent variable increases, there is equivalent increased probability of falling at a higher level on the dependent variable, which in our case is what we're calling as the operational performance. So this is the most important table, because this is the table where we are actually trying to assess the significant effect of each and every independent variable onto the dependent variable. So in this case, therefore, we are going to do what we call take one independent variable and give it what we call the relevant interpretation that is needed in this case. And we start with what we call technology. So now, in technology, is it having a significant, because that is the way we need to frame our statement, is it having a significant positive or negative? Is technology a significant positive predictor of operational performance, or it is non-significant positive predictor or negative predictor? What can you say about technology? What is the significant value for the technology? Is it greater than 0.05 or it is less than 0.05? Can somebody tell me that? Hello? What can you see? Is technology is a significant predictor or it is non-significant predictor of my dependent variable? Yes?
I'm saying I'm not seeing that screen that you're talking about. I'm seeing the one that was showing pseudo.
Under location. Okay.
Trans L, the level of technology.
Yes, L is the level of technology.
So are we reading under SIG 7.788?
Yes, it is 0.788. It simply means it is non-significant, isn't it?
Non-significant, yeah.
Yes.
So it is like all my, it simply reflects that all my independent variables in this case are having non-significant contribution to the dependent variable. So now you shall assist me to, now we are starting with what you call level of technology. The level of technology was not a significant predictor. Level of technology was not a significant predictor of operational performance in this company. Now, that is how you begin by framing your sentence. Then now we go to the details of bringing in the value that we are able to read there. Now, for every 1 unit increase, what is happening? Because there is a negative sign there. Yes? What did I tell you?
Decrease.
There is a
decrease. There's a decrease.
Of the log odds?
2.214.
Yes, that's okay. Then you go to supply. Supply also is not a significant predictor of the model. So we talk about for every 1 unit increase on supply, there is predicted decrease of 0. Is it positive or it is negative?
It's positive.
It's positive, isn't it? So
1.076.
if it is positive, now there is no decrease, but there is an increase on the odds.
1.076.
Yes. Then we go to marketing. Then in marketing, what do you do in marketing?
Positive.
What is the value?
0.361. 0.361.
Is it positive or negative?
It's positive.
It's positive. So we are saying marketing was not a significant predictor of operational performance. Yeah, marketing is not a significant predictor of operational performance. Then we say 1 unit increase in marketing, there is a predicted increase on 0. What is the value there?
361. 0.361.
0.361 in the log odds of yeah
0.862.
yes. So we then quality, we also do what we call quality. We bring first, we check this the sign in quality, try to look at that sign. Is it negative? What is positive?
It's negative, so it's a predicted decrease.
Yes, that is decrease. That is decrease. So, and it is non-significant. So we simply say quality was not a significant positive predictor on the operational performance. Then we say 1 unit increase in quality result to
Negative.
there is
Negative
predicted
6.27.
decrease of the value in the log odds on operational performance. Then that is quality is our final variable, and that is what you present in your report. Now, the so-called ordinal
So,
legislative.
in short, you are saying you have to give the estimate figure and the sig figure.
Yes,
while
you
reporting.
must be able to talk about two things. One is
Yeah.
whether the contributor of the independent variable has a significant contributor, or it has non-significant contributor to. So we must mention significant. You must read what you call the value you are reading in the significant column. So we might say the technology was a significant positive predictor on operational performance. Then you bring in there was a predicted increase, as whether it was negative or if it is positive, then we simply say 1 unit increase in technology result to predicted an increase of the odds, log odds 0.026 in the log odds of. So that's now how the interpretation is supposed to be done. But if we have a negative estimate, value there is negative, simply means that there is a decrease. It's a decrease. There's not an increase. And that's what now you present in your report. And that's now become like the final part on what we need to interpret. So now the last column we go to is what you call test of parallel lines. I don't know whether we have it here, test of parallel lines. Okay, I never clicked it. So when we were running that, we needed to click the test of parallel lines. Now we can use another approach to be able to run ordinal logistic regression. This approach was simply going through what you call the menu of analyze, regression. Yes, analyze, regression. Let me take you first of all to the SPSS. So we can use two methods. We can actually most 3 ways by which you can do it, but I can just explain the second approach. So apart from the analyze menu, where you go to regression and you come and go to ordinal, we can simply come to analyze, and then you go to general linear models. General linear models, because remember, ordinal regression is one of the general GLS models. So we can use that column to be able to run this. So simply what we shall do is analyze general linear models, come to general linear models, then I come to general linear models, then I come to type of model. So I choose the type of model that I want to model now, and the type of model that I want to model is ordinal logistic. You come and click ordinal logistic. We have ordinal probit and also ordinal logistic in SPSS. So once I've already done that, I come to what you call the response. I bring in the dependent variable. So my dependent variable, I bring it in, and it was P here, transformed P. So I bring it in, that is my dependent variable. Then I need now to go to the predictors. I need now to go to the predictors. In the predictor column, we have two, you have two columns here. We have factors and we have covariate. We said that covariates are the continuous variables, continuous variable. And then the factors here, I will put the categorical variable in my model. And the categorical variable here was gender. Gender was the categorical. Even if at all I have, remember, in most of the research questions, the demographic information needs to fall under these factors because most of them are categorical in nature, like even level of education. You may find that now that level of education may have different categories, like even postgraduate, undergraduate, diploma, and even lower levels. So that you may have different categories. And then covariate, like in this case, we are presuming the transformed values that we got after we are getting the mean of adding the sum of the 10 questions that we had in the Likert-Scale. We are assuming that they were transformed to be a continuous variable. And that's why that is the basis of using Likert-Scale for running multilinear regression. That we presume we are now dealing not with ordinal, but we are dealing with a continuous variable. So we bring them as the covariates. So I shall bring all of them as my covariates in the covariates box here. The first one is L. I have S, I have M, and then I have S again. And then the last one, there are four. There were four variables in this study. So I bring them as my covariates. So once I've already done like that, I come to model, I click the model. So in the model, I want to bring all these variables in the model. I bring them in the model. I think you then now I come to the estimation. So in the estimation, I need to identify what are some of the estimates that I will be performing. One of it is perhaps if I'm interested in changing the log likelihood. Yes.
Huh?
Yes. And in the enter minimum value for the following values. So where is the minimum value? Change in the log likelihood absolute value. So now the minimum value here, perhaps let me talk about 0. Okay. Then statistics, then all this, what has been ticked, case process descriptive model information, goodness of fit, model summary, parameter estimation. I'm looking for test of parallel lines. Where is it? Interaction, include exponential, covariance. Okay. Then I need to move to I think that is the maximum that I can have now. Then I come and say okay. Then when I come, I say okay, under GLM model, I will find the following. I need to transfer you to see what the kind of data that I've already intergenerated here now. Okay, I have goodness of fit. Which we require to interpret. Then representing the model summary, I will have what you call omnibus test. And then I also have test of model effects. And then the parameter. The parameters may not change different. They might almost be the same. Like if you look at all the parameters are non-significant, just the same way like the other time we are doing the interpretation. Then I have what you call the B values. Yeah, you can see the B, which we are using to talk about that coefficient. Now, when we are in multiple linear regression, then we use the B column for developing what you call the model equation. Yeah. So in this case, we are still also going to use the B column for interpreting the log odds. This one we are calling them as the log odds. Yeah, because this is a probability model. So you find that now the interpretation may not differ so much with what we already done using the other method. So the method which looks a little bit better for you is perhaps the one that you will go for, but the interpretations are the same. The interpretation are the same. So we can simply do what? We can simply open up for questions so that we can have interaction right now in the class. Now we are just generated the same. So the interpretations are going to be the same, the way we are interpreting the goodness of it. Our model in this case is going to be what we are calling as the omnibus test. And we are talking about the likelihood ratio of the chi-square test that we saw in our root 1. Okay, so that's okay. So we can open up and then we can be able to discuss. Remember what I prepared, what actually I prepared for us to look at was a situation whereby we are running a multilinear model and we have one categorical variable like gender or religion in the model. We were trying to insert something like gender in the model so that we were able now to see how the operations were to come. But now this was only possible if at all my Likert scale was supposed to be proved past the normality test. Remember, my Likert scales questions, when I computed, it failed. So once it failed, I don't have any otherwise but to go and test or to go and run appropriate model, which is called ordinal logistic regression model instead of multiple linear regression model. If at all I satisfied what we call multiple linear regression model normality, then I was supposed to take you through a step of running what you call multiple linear regression model with a categorical dummy variable. That is what I prepared. Actually, that is what I prepared to present. But it's only that now the data set, when I was testing, it failed. So when it failed, I had now to change the analysis to go to ordinal logistic regression model. Now I'm not talking about multiple linear regression model. This is the same practical scenario that I'm telling you, that data analysis depends on two things that are very important. And one is the research design. How more knowledge you are going to have in analyzing different research designs now put you at an upper level of understanding data analysis. Number two is the so-called nature of dependent variable. Like, look at this case. We prepare to run a multiple linear regression model, but because we have failed normality, we have tried transformation with even logarithm, which is a more powerful transformation, it has failed. We have still found that the data is not normally distributed. You cannot force it. You have to now choose appropriate model that fits in, that you can be able to run. And we have gone for what you call ordinal R regression, ORL, instead of testing on OLS, which we were supposed to run after we were with a dummy variable, with what you're calling as a dummy variable. So good and so well. You will realize that now you cannot fix, and this is now the misconception that most of students end up, that you give your data to the so-called data analyst, and then he cooks for you the data. Like, for instance, if my data failed normality, I cook and then I indicate the figures that were indicating that it is it's not normally distributed, I come and change for you. I put now, instead of 0.00, because I know in the normality test, I'm looking for an insignificant value. Therefore, I come and put for you 0.71, simply reflecting that the data set originated for normal distribution. Then I go and run what you call multilinear regression. And if I run it, you will find that the results are actually not agreeing. So once the result is not agreeing, they cook for you again. So the only thing that you paid your money for is for your data to be cooked, which you can also do on yourself. And you do everything. I don't pay any amount of money. So students are looking for shortcuts. That's why you go and pay somebody who only learned about one model. So if it fails, they cook. So look at this case. Now we decided now to go for ordinal logistic regression model because of failing the assumption. So when assumption fail, not necessarily will you find these data that are being collected from the fail. You will find more often than not that the assumptions are failed. So when assumptions are failed, you need to choose appropriate model. If, for instance, that I'm not dealing with what you call ordinal, like for instance, I'm predicting a political party that a person may vote in 2020 based on some key independent variables. And then we have 5 political parties. So remember, I'm supposed now to run what you call multinomial logistic regression. Multinomial logistic regression. And remember, up to this extent, there's no researcher that has supported the fact that nominal variable can be treated as a number like ordinal. It is only ordinal that can be computed as a number, and then we run what we call a nilly statistic, parametric statistic used based on it. But when my data set like a political party, predicting a political party a person may vote for based on age, based on religion, based on another factor like ethnicity. Those are the variables that you have, and you want to predict a person's chance of voting a given political party. You cannot run any other model other than multinomial logistic regression. You don't have other ways of running. You cannot even talk about multiple linear regression model because the data set is, the dependent variable is coming in nominal variable. It's a nominal variable. But when the dependent variable is ordinal, ranked response, then we have a possibility of using it as a number by doing all this, but only if I've met assumption of normality. And these are the assumption of homoscedasticity and assumption of linearity. Remember, if assumption on normality is met, there's high chances for these other assumptions to be met. So the most important assumption that you must give as a priority to test is normality assumption, and also assumptions on outlier. Remember, assumption of outlier is very easy. I've introduced you in this class to a second way of testing for outlier, which does not necessarily require you to go through what you call the graph option. You just simply go to explore, bring all the variables to what you call as a dependent variable, and then click what you call normality with plots. And all the assumption tests will come. One of it will be on the skewness and standard error. We'll also get QQ plots. You shall get histogram, and then you shall get now the most powerful statistic, which is called the normality with test, the p-value, the significant p-value. And in that case, you will make a decision, which can I run? Now, it simply means that once you have written your proposal, you may propose that you are going to run multi-level linear regression and put on those variables and do all your factorial reduction. But when you now come, because remember, you have not collected the data. When you now collect the data, you will change and now start running ordinal logistic regression because the assumption was not met. You cannot force yourself that the way you proposed you are going to run multiple linear regression is the way your analysis must go. Because if at all assumptions have been met, that is when you can do it the way you proposed. If it is not met, then you now need to change to adopt the appropriate model that fits in that particular case. Okay, so now we can do what? We can open. We have taken the number of hours that we are supposed to take for this class. This one was